Hey everyone. Today I'm going to talk about something called node voltage analysis. Now I feel like I say this every episode, but this is the most important technique you will learn in electrical engineering. Seriously, professional circuit designers use this every day. Modern circuit design is done using software-based simulations that fundamentally use differential equations in linear algebra to solve circuits as matrices composed of node voltages and currents. Okay, whoa, that was a lot of words, but I'm going to talk about what I mean when I say node voltage and node current. And so the motivation here is basically that, combining circuits into equivalent series and parallel models just doesn't apply in all cases. For example, if you look at the circuit that I have drawn here, you can probably start imagining combining this in various series and parallel forms. But what would you do if I added an element here? Now think about that for a second, but I'm sure you're going to realize very quickly that there isn't a good solution anymore. There are no series or parallel elements that you can just combine and model. So the whole point of node voltage analysis is to give us a general approach to solving circuit problems that will work in every case, even when our convenient shortcuts aren't possible. So let me go ahead and annotate this circuit, and then I'll prep a quick example. I've gone ahead and labeled this circuit with resistances 1 through 5 and corresponding voltages 1 through 5. And a V source here. I know that S kind of looks like a 5, but this is Vs. So up until this point, we've generally used Ohm's law and parallel and series combinations, also with Kirchhoff's voltage and current laws. Node voltage analysis is really just extending or applying Kirchhoff's laws to more complicated general case circuits. So I can't remember if I've done this yet in any videos, but I've included here an extra symbol in this circuit. This is called ground, and it may or may not be a physical thing. Sometimes we just apply this as a tool in our analysis to make things easier. So let me talk about it in that sense. The reason node voltage analysis is sort of hard for some people to grasp is because we really take an intuitive step away from the concept of what voltage is. So I've talked about this before. Voltages appear across circuit elements. A voltage is a potential difference, right? So a single point in space or a node can't actually have a voltage. There's no meaning in that. But what we do to simplify our analysis is we choose a reference node, and it doesn't have to be, but it's usually where the ground is. And again, this circuit may or may not actually have a ground. You can still just choose any node to be the reference, but sometimes you just draw a ground on a node and say that's going to be the reference node. And all that means is that when you're comparing voltages between nodes or assigning voltage across elements, you'll usually refer to whichever node is ground as having 0 voltage. And that really just simplifies a lot of computation. So it's really just an analytical tool. And let me give sort of a cheesy example here. So if I pick this node and put a little dot there and call this node X, I'll also label another node. We're going to call this node Y. What if I wanted to write V3 as a function of other voltages in this circuit? Well, I might use Kirchhoff's voltage law, for example, to write V3 in terms of V4 and V5. Now, if you remember Kirchhoff's voltage law, I can look at any loop in the circuit, so I can ignore all this other business and just look at the loop of resistors R4, 3, and 5. So it should be pretty easy to see that V3 equals, if, given the way we've assigned our voltage polarities, V3 should equal V4 minus V5. And this is, totally familiar. There's no departure here from anything that we've done so far. We're looking at voltages across elements. But so really, what is the voltage V4 and what is the voltage V5? What we're doing is comparing the voltage on two nodes and taking the difference and saying that's the voltage V5 and that's the voltage V4. So really, voltage is only a difference between 2 points. But it can be, nice to talk about it as appearing at a point. So if you say the voltage, quote unquote, of the reference node or the ground is 0, then what that means is every node in the circuit or any place that I've drawn a dot has a voltage as referenced to 0 or referenced to ground. So think of it this way. If you start at 0 volts and then step up by the voltage V4, that means that node Y has a voltage that's V4 volts higher than 0. Right? So because this reference is 0, I can write something like Vy, or the voltage on node Y, equals V4. And really what's happening there is I'm saying Vy equals 0, starting at ground, and stepping up by V4 volts plus V4. Really nothing crazy, nothing flashy going on here. I'm just saying that really what's going on here is I'm treating each node as if it is a voltage or it has a voltage, even though in reality voltages only appear across individual circuit elements. You may or may not know the value of certain circuit elements and voltages or currents or powers through them, but you might know some. And basically the point of this type of analysis is to break down the circuit, label each node. So there would be 4 nodes in this circuit: the ground reference node, node X, node Y, and then I guess there's another node over here that I haven't labeled, and we could call it node Z. Vy is really just V4. In that same way, Vx is just V5, right? And also Vz is just V source. It's whatever the source voltage is. Assuming that this is ground here, you just step up by the source voltage, and that's the voltage on on that node, as people will say. So you might be interested in finding the voltage Vx as a function of maybe Vy or Vz. And that's a similar concept that we've dealt with before, but you'll find that things just become potentially easier as you move into complicated, messy circuits. Where node voltage analysis becomes extremely powerful is when you realize that the voltage across any circuit element is the difference between the node voltages that surround it. So for example, in this circuit that I just drew, I added this element R1 here, and I said that it was really obvious finding Vz and Vx. We know those voltages immediately. I said that that Vx just equals V5 and Vz equals V source. So then I can very quickly find the voltage V1 by taking the difference between the node voltages that surround it. So let's follow the polarity that I have drawn. So then V1 would equal Vx minus Vz, which equals V5 minus Vs. And these are allegedly known voltages in the circuit, V5 and Vs. And then given that we know V1, and you have a resistance there, some circuit element there, then you supposedly can solve for the current and power and so on. So this is, again, a very simple example, but you'll find that this is a powerful tool moving forward, and I will likely make a video on this, but you can essentially look at any circuit like this as a matrix of parameters and solve it that way. As circuits become more and more complicated, this just becomes a lot of arbitrary computation. And it's very clean and nicely wrapped up in a matrix. So with that, that's probably all I want to cover in this video. I think maybe next I'll do an example. We will see what comes in the next video. So thank you for watching. Have a good day, guys.